Let's start with a little bit of review from last time. And I always like to do this, as I said before, to kind of go over and over and over things. Remember that there were 32 registers, starting at R0 and ending at R31, that the last register, just for being handy, always had the value 0 when you tried to read it, and you could write whatever you wanted to it and it would just disappear. The second thing that we talked about was that there was a big memory that had the instructions in it, and this program counter register had an address in it that pointed to where the next instruction was to come from. And then what the computer did every time it wanted to execute an instruction is it would find out what was in the program counter, fetch the instruction that's in that location that the program counter points to, increment the PC, execute whatever that instruction says to do, and then just repeat that loop over and over again. And so we sequentially go down the different instructions of a program and actually do it. Now again, by review, there were two kinds of instruction formats. One used 3 registers, one used a register and a constant, and then the destination. And if you remember, we were very careful to make this easy to understand. It always went from left to right. So the contents of this register and the constant were operated on by whatever the opcode here said to do, and the result was put into the register indicated by register C. In a similar way here, the contents of register A and the contents of register B were operated on by the opcode here, and the results were put into the contents of the register indicated by RC. And what sort of instructions did we have? We had very straightforward ones like add, subtract, multiply, and divide. We had the constant versions of those, which used this format of instruction as opposed to this one. We had logical instructions like AND, OR, and XOR, and also things like shift left and shift right, and different things for doing tests before we do a branch like compare if equal, compare if less than, compare if less than or equal to. So this is, again, just by way of review. And again, when you do the problem set, which is about to be handed out, you'll actually get a lot of experience doing this. Finally, we had 2 other instructions which were being used in order to send data between the register file, which was small and fast, and the big main memory, which was kind of slower, which were called load and store. And again, to remember which way they go, take the viewpoint that you're sitting there in the processor next to the register file, and you think of the big memory as being out there. And so load means to bring something from the big storage into your small register file, and store means to take something from your small file and to put it into the big store. And so if you remember, the key idea here is that it summed together the contents of a register with a constant in order to get an address to use pointing into the big memory. And that address was used for both loading and storing, and that allowed us to do all sorts of tricks in terms of finding out exactly where in the big memory we wanted to load or to store things. Okay, finally, by way of review, how to do a branch. It's a little bit different than it was in the scheme register machine language, and the difference here is that you get to choose which register is used for the condition register. It's not always one hidden place. Rather, you get to say branch if the contents of register A is 0. BRZ means branch if 0. BRNZ means branch if not 0. And so it looks at the contents of register A, and if so, it adds a displacement, which is calculated from the constant that's right in here to the contents of the program counter, and it branches forward or back. And finally, there was a second form of jumping around, of changing the program counter, and that was called jump, and that was very straightforward. It jumped to the contents of register A. And I told you I'd be telling you about what register C was used for in this lecture, and in fact that's just what I'm going to do, but not on this slide. This is just showing you what we did the last time. Okay, so let's review how you actually use instructions like this to do an iterative version of factorial. So if you remember, iter looked like this. We had n and val. If n is 0, then we return the value val. Otherwise, we multiply val by n, subtract 1 from n, and go back and do it all over again. And we're assuming here at the beginning that n is 20 and val is 1. And this was that final optimized version of code that we got to at the end of class last time, which basically said, well, let's take n, load it from the big, slow memory, and put it in the small, fast register file, and let's choose register 1. We could have chosen any register that we wanted, but R1 is just as good as any other. And let's go ahead and put val into R3, and that's fine. And now let's test R1, which is n, to see if we're done. And if it is equal to 0, then we branch to done, which is down here, and everything is finished. Now, of course, if it's 0 right off the bat, we actually don't need to do any work at all, so we could have branched to down here, but you'll see why this done is down here where it is, because in most of the other cases where we don't start out with n being 0, once we're done with this loop, we have a little bit of housekeeping to do to store n and val back in the main storage where they belong. So now we have n and val in R1 and R3, and we increment, we multiply n by val, putting the result back into val. But it's not the final version of val, which is in the slow, big memory where we put the result. Instead, we're only going to be doing this inside the small, fast one. In a similar way, we subtract 1 from the place in the register file where we're storing n and put the result back in the same place. And then we test whether R1, which is the small, fast copy of n, is not equal to 0, and if that's the case, we jump back to the loop, and then we just keep doing this over and over again. And this is a very compact set of 3 instructions here to get the job done. Finally, n will eventually get down to being 0, and this test will fail, and instead of jumping back to the loop here, we will just continue down to here, and so we will have finished executing this loop. N will be 0, val will be whatever n factorial is, or was, given n from what it was before, and now we have to store away the updated values of n and val as if we had done, if you remember, the earlier version of this code, which every single time in the loop would do the transfer from the main memory into the small, fast register file, do the work, store it back, and then loop. But we decided to push those outside of here so that we could do this thing faster. And most compilers that will compile code that looks like this will do an optimization such as putting loads and stores outside of tight loops like the one that you see here, so that these run as fast as they possibly can. Okay? Are there any questions as to kind of where we got to in the last class based on this? Yeah?
You can use variable names, but not for these fast registers? You always prefer those as R1 and R3 and so on?
Yeah. In general, let's see. I could have put down n is 1 and val is 3. Okay? I could say n equals 1 and val equals 3. That's different than what I just did here. And what that would do is, and I'll talk about how that works, is associate the symbol n with the constant 1 and the symbol val with the constant 3. And instead of using the word R1 or the word R3 here, I could have used n and val there. Okay? But in general, that's not done, because we think of the registers as being kind of a scratch pad of multiple uses. Like at one point in the program, we expect R1 to represent n. Very soon, however, we can expect R1 to represent something different. So rather than try to mix things up, we just always call it R1. However, this location here is a location in the big, slow memory, and we say that here there's a word which has the value 20 in it when we start off, and the address of that word is given the name n. The address of this word that has 1 in it is given the name val. And so when I say load n into R1, this n turns into a 32-bit excuse me, that n turns into a memory location where I will find the value of n. And that's what gets put into this load. And I'm actually going to spend some time talking about exactly how that works now. So to answer your question even more thoroughly here, what we're going to do for just a little bit of time before I talk about how the stack works is I'm going to talk a little bit about how these tools work that you're going to use to assemble programs that are written in the beta assembly language and turn those programs over here into a set of bits, a stream of words, which get loaded into that big, slow memory, and then the program counter goes down these words and execute these bits of code. So we want to understand what's inside of this box. And this is just a piece of software, but you're going to be using it, so it's very important you understand how it works. Well, it turns out this program itself is actually composed of two parts that run in series with each other. The first part is called a macro preprocessor. Okay? And how many of you have used macros of any sort in Word or PowerPoint or Excel? Okay, so you guys generally have the idea of what these things are for, right? They're handy little shortcuts, so you don't have to type the same long thing over and over and over, okay? The second thing that this has is a piece of software which can understand values associated with symbols, and we'll talk about what that is. And finally, a little thing that can evaluate arithmetic expressions that evaluate to constants. And we'll talk about how that works too, okay? This is for doing things like 1 plus 2 and coming up with the answer 3. And this is for doing things like let x be 7. And in the future, let me refer to x as opposed to having to write 7 down each time, okay? And that's what's going to go on in the second half of this thing. Like the macros you've used in many other types of pieces of software, we have a set of macros which you can write dot macro, and then you write sort of a function definition like that. This is consec4, parenthesis n. And the expansion of the macro is defined as n, n plus 1, n plus 2, n plus 3. Now, if the assembler hits a line like this, it swallows it up and remembers the definition of the macro. Okay? It doesn't output anything. It just eats this up and says, okay, I know what the macro consec4 is. Then in the future, if you put in a line that says consec4 of 37, it will, inside of itself, execute the macro and replace n, n plus 1, n plus 2, n plus 3 with the text 37 going in for n, 37 going in for n, 37 going in for n, and 37 going in for n here. So what will come out is 3, 7, 3, 7 plus 1, 3, 7 plus 2, 3, 7 plus 3. It's important to understand that this is purely lexical. It's only text. The macro part of this system does not understand the meaning of the characters 3 and 7. They're just letters, okay? So it's just putting this little string of 3, 7 in place of n, 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 and n, and then spitting out exactly the macro that you told it to do with the substitution of 3, 7 for n.
So,
and so this will get,
or in the parentheses.
then this would be house, house plus 1, house plus 2, house plus 3. Yes, it could be anything, okay? So that's all that it knows how to do. And what you'll find is that this assembler and the macros we use here are more simple, I think, than any other one that you've ever seen. Okay, it's the bare minimum of what you need. Okay? Now, macros are terrifically wonderful for defining certain beta instructions. So for instance, when I say add RA, RB, RC, add C, load store, things like that, these are actually macros that are defined in a file called beta.uasm, okay? And when you call them, it just invokes the macros and substitutes in whatever you write in the parameters here for the definition that it has. And I think in one of these slides here, let's see, let me see if I can find one here. Okay, here's a macro. Okay, now it's a little bit hard to show, but the definition of the macro brnz is defined to be another macro, which is also in the code that you have to look at, which is called beta opc. And that macro knows that the opcode should be hex 1e, RA, this stuff over here, which we'll talk about in a second, and R31. And so what happens is that it expands this nice little word that you write here eventually into an expression which will turn into the actual bits that get used in the output. And if you look at macro.uasm, let me just look here just one more time here. Okay, it looks like we don't have it here, but if you look in the references that we've given you from the last class, you'll actually see the definitions of the macros, and they should make some sense. Now, After the macro preprocessor has done its job, the next half of the micro assembler, or the beta assembler, is something that knows how to do math, okay? And it only knows how to do very straightforward math that turns into a constant. So for example, if I type in 37, after the macro preprocessor, the tool knows how to compile the number 37 into a set of bits, which will then go out into whatever the program is that we're trying to make. It also knows about certain formats like 0b, meaning the thing that follows is a bunch of bits, or 0x, meaning the thing that follows is in hexadecimal. Okay, so you can use these forms if you want to as well. It also knows, as I said, how to do very straightforward math. So if I say 37 plus 0b10 minus 0x10, that will be evaluated and will return a 32-bit constant, which will get spit out of this tool, which will then go into the stream of instructions to be executed. 24 minus 1 is 23. 4 times binary 110 minus 1. And here we have an AND sign, which is for the logical AND of the bits in here with the bits in here. And so those will go out also as well. And it turns out that each of these four things is, if you were to figure it out, equal to the decimal value 23. Okay? So the assembler really so far can only do two things. It can figure out macros and it can do simple math. But there's more. Okay? It also has this third trick, which is that it can understand the assignment of values to symbols, and then you can refer to the symbols and get the values back out. And this sounds like a macro, but it's a little different, and I'll explain why. So let's say I say x equals 1, y equals x plus 1. So far, nothing gets spit out. Okay, now notice this is not dot macro x1, which would say the macro x has the value 1. It's a similar sort of thing, but not exactly the same. Y equals x plus 1. So now if I say add c x 37y, the x will be replaced by the value 1, and the y will be replaced by the value 2. Okay? And what will come out here is that, put register 1, add 37 to it, and put the result in register 2. This is different than what we talked about just before with macros, in that this is not a textual thing. These right-hand sides get evaluated right away to figure out what the value of y is. In other words, y is not the string x plus 1. Y is the number 2. Okay, and that's one difference. Let's talk about another difference. A macro, if I have a macro foo, it turns out I can redefine foo several times in the file. And so the question is, what is the value of the macro foo? And the answer is, it's the value that it had the last time that I assigned the macro. Okay, so in this purely textual substitution mode, I can say dot macro foo of x, and I can say x plus 1. And this can go down like this, and then I can say foo of 3. And then I can say dot macro foo of x, and I can say x minus 1. And then I can say foo of 3, etc. Now what comes out of the assembler, which again is composed of the macro preprocessor followed by the part that does the work with symbols and the evaluation of constants, what comes out of here is absolutely nothing. Okay? It just remembers the definition of the macro foo. Then other code goes, and then finally it hits this piece of code, and it says, aha, I know the macro foo, so instead of 3, I'm going to put out what? 3 plus 1. I don't understand what 3 plus 1 means, but I'll substitute for x 3, and I'll put out the string 3 plus 1. And then I'll keep on going, and now I come across the definition of the macro foo again, and it's different. So I will remember that. Then I'll come down here, and then this foo of 3 will come out. And then what will I do? 3 minus 1, okay? So that's how that works. Different than that is the idea that I say y equals 3 plus 4, okay? Now, as I said before, there's sort of two separate parts to this thing. Here's the macro preprocessor. And that feeds into this thing which is the symbol resolver plus constant expression evaluator. And that finally outputs things. Now when this 3 plus 1 goes into here, what do you think pops out? 4. Good, because in fact the constant expression evaluator figures out that that's 4. When the 3 minus 1 pops into here, what pops out? 2. Okay, good.
So where exactly is the symbol resolver plus constant eval? What is this last thing?
These are just two pieces of code that are run in series with each other on whatever you write. So if I write this text here, and I say assemble that text, what it does is it first does this on that text, and then this intermediate data goes to the second half, and then the output goes into a file.
Anything to make it do that second
No. It just does one and then the other one, right? It's one call to say do it, and then it just does one and then the other. Now let's talk about this though. This goes into here, and this guy doesn't see anything special about this at all. So what comes out of here is the string y equals 3 plus 4. Okay? And what goes on inside of here is it remembers y has the value 7. So it has a little table of symbols. Okay. Then in the future here, I can say y, and this goes through here, and this comes out here as y, and then over here it comes out as 7. Now so far you still don't know why you'd prefer to use a symbol instead of a macro, but let's actually keep going and we'll see. Big difference here. A symbol's value throughout a file is the very last value it was assigned in the file. And that's kind of strange. What it actually means, and this will kind of blow your mind here, is that I didn't have to put this up here. I could actually refer to y over here and put down y equals 3 plus 4 all the way down here. Okay, and that's different than a macro. In fact, what this guy over here does is he takes 2 passes through the data that comes in through here. The first pass is, let me figure out all the definitions of the symbols that are here. And let me fill the table up with the definitions of the symbols. And then the second pass is, let me go through the file again and resolve all the symbols that are asked for and fill them in with the values that they have. And guess where this is going to come in handy? Well, what if one of the things that I put in here is branch label 1, and I put over here label 1. Well, it turns out that label 1 is sort of a shorthand for saying I want the symbol label 1 to have the value of where the program counter is right here. And notice that this definition of the symbol label 1 is after the use of the symbol label 1. And thus we have to go through the file at first and find out where all the labels are, and then go through it again and fill in for every time that they're used where they ended up being. Okay? So we're going to talk about exactly how that's done too.
How does it work when you said it goes 2 passes, the last one? Because once it goes through the macro process, I would know what y is. So why does it go two times?
Well, let's see. Let me do this the right way. If we move the y equals 3 plus 4, then that's not there anymore. This happens way down here, y equals 3 plus 4. All right? And then what happens is that all this stuff gets stored in a temporary file. And then this software here goes through that file once, doesn't output anything. But as it goes through it once, it looks for things like y equals 3 plus 4. And it stashes away the association between the symbol y and the constant 7 in a table inside of itself. Then it goes back to the beginning of the file, and the second time around it doesn't even look at things like y equals 3 plus 4, but when it does see y, it says, aha, I know that's 7. Because the last time I went through here, that was 7. So this is a two-pass system here. Okay. This thing over here is just one pass.
Why don't they combine into a total of 2 passes?
Where you have both of them working at the same time?
Macro would fill in and build up a symbol table, which would then get resolved.
It really doesn't matter. So I am talking about how you should think about how it works. You could build this thing in many, many different ways.
But it physically makes 2 passes.
It has the effect of making 2 passes. What it actually does doesn't really matter. and I hate to say that. So one could imagine an input for which it could be smart enough to know I don't need to make 2 passes, because all of the symbols were defined before they were used. But if it needs to, if a symbol is not defined when it's used, it says, oh, well, I don't know what that is yet, so let me look forward to find out where. You see, I could talk about this as the thing looks forward for finding what it needs to know when it doesn't find it in the past. Or I could say, no, it really makes 2 passes. And the implementation is, if I want to do it a simple way, it will make 2 passes. It makes 1 pass and doesn't try to do any work at all other than to remember the definitions of symbols. And then it goes back and makes a second pass and doesn't look at the definitions anymore, but just fills them in. And that's the effect that the thing has. But whether it actually does that or tries to be more smart and only make 1 pass but peek ahead a little bit, that doesn't matter. And I know it's not a good answer, but that's actually true. Okay, so it turns out that there are techniques for faking 2 passes with only 1 pass. Okay, by cheating and looking ahead and doing stuff like that. And different assemblers do it in different ways.
So. The label 1, is that a symbol or is that something completely different?
It is a symbol. It is not anything different. And that's actually what we're going to talk about next. So the repercussion of a symbol being the value that it was at the last time it was defined in the file means that we can make forward references to symbols that haven't been defined yet. And then we just talked about this, how it has to make 2 passes, one first looking at the definition of all the symbols, and the second time going back and filling in what the values are. So now let's talk about labels, like I just did right up there. One way that I can say to branch to a loop, I can say branch, depending on the value of R3, to the location loop. That location is a symbol which I can define by saying loop equals dot. And what does that mean? Well, it turns out that inside of here, there is a symbol called dot. And this symbol has the value of where we are in the output file. So what does that mean? Well, as this produces code, and remember, this code will get executed eventually in the computer, 1 word at a time, there's this idea of the present location in the output file where we're outputting stuff. So it starts out at location 0, and it builds up. And this value dot is the very next place where we're going to put something out. And so an example is, if I say loop equals dot, what I'm saying is make the symbol loop equal to the value of where we are in the output file where we're about to put out the instruction add C. So let's say we're about to put out an add C, and add C is going to be a bunch of bits, which I don't know off the top of my head, right? But let's say that this means add C. Well, before we hit that line, dot is pointing to the distance between the beginning of the program and where that add C is going to go. And it turns out that that is a good way of keeping tabs on where that instruction is in the program. Now, if we go down later, one way of making sure that where we really branch back to is back to here is if the value loop actually was a pointer to here. And one way of doing that is to have a statement like loop equals dot. Okay? So again, dot is an offset where we are in the assembler and outputting the code. And when we say loop equals dot, it says put the value of where we're about to output this line into the symbol loop. And then down here we can branch to loop, and that makes sense. Okay?
There's the way you've shown it up there, it looks like dot is being used as a symbol, right? Now you've said that the symbol is the last throughout the program. It's the
Absolutely
last
right.
definition,
with the exception of dot.
loop.
With the exception of dot. Okay, now, and I know that that's gross, okay, and it shouldn't be that there's things that are different, but it turns out dot is, I think, the only one that is different. Okay? And dot is not something that, so dot updates itself all of the time and is different in different places in the code.
Okay.
Whereas the other ones, there's only one value throughout the code. Okay, sorry. I wish it could be different, but it turns out this is an elegant way to do things. And actually, this is a very commonly used thing. The dot is the next place, the location of the next opcode that is about to be put out. Okay. Now, if you think about it, you may remember that the dot, that if I were to branch to here, how is the instruction for branch actually done? Well, let me back up a second. Let's look at the instruction for branch. Somewhere here.
It's forward.
Forward a few, right? Store load branch. Okay. PC equals contents of PC plus displacement. And if you remember, this displacement is this 16-bit quantity that's being put here in the center. So this is a little bit disconcerting because we have 16 bits that are telling us how much to add or subtract from the program counter when we hit this branch right here. So the program counter, contents of PC, will point to here. And if you really think about it carefully, the program counter, in fact, before we execute the branch, it increments to the location of the next opcode, and then we execute the branch. So here's where the PC is. And what I want to do is, if I branch, I want to subtract a distance from the PC. I don't want to subtract whatever the number is for how far this distance is. I want to subtract this distance. So how can I make that work? Well, it turns out that in the macro definition of branch, all of the right magic happens. The macro definition of branch says, if I give a label here, in this case it's loop, which is an absolute location of where in the output file I want to branch to, the macro says, take that location, subtract dot from it. Well, which dot is that? That's the dot down here, where the program counter will be when this code runs. Because remember, the program counter, when the code runs, will have skipped to the next place and be sitting here. And it's going to subtract loc, which is going to be this loop here, from this, get a distance, and it turns out you have to subtract 1 from that, one more than we want to be as opposed to being here. So there's a fence post thing, but you don't need to worry about that. That's what the -1 is over here. But the key is that it calculates in the macro itself what the distance is between where we are and where we want to branch to. And that is the actual number that gets put in to the set of bits that represents BRNZ. Okay, and so here you see the handiness of having a macro preprocessor, a symbol resolver, and something that can actually figure out the value of these expressions as well. And so anyway, this ends up getting compiled to a set of bits that has a field in it which represents the distance from here to here.
You use loop colon in that one program.
Okay, yeah, that's absolutely right. Well, it turns out X colon, this is like I paid you to ask these questions. X colon is an abbreviation for X equals dot. Okay, that's all that it means. Okay, so when you say X colon 0, what does that mean? X equals dot, and now put out a 32-bit constant 0. Pretty cool, because when we think about it, what is this really trying to tell us? We're reserving in the big memory of the machine a 32-bit word that we're initializing with the value 0. And we're also keeping track of where that word is by saying x equals dot before we put out that word. And so x will be the location in the big memory where the 0 is. And then in the future, we can say load x into R0. And that will load the location with the 0 in it into R0, do something, and then store it back. And so x colon is good for not only a label of where we want the PC to jump to, but also the label for where we want to put data. So anytime that we want to put a piece of data in our code, all we have to say is, you know, I want n to be 4, n colon 4. And then I can write some other code. And what that will do in the output is it will reserve a single word with the value 4 in it, which is 100, right? And in the symbolic memory of this part of the assembler, it will remember that n is wherever dot was when we put this thing out, which is the location in the memory right there. So n will point to there. And then in the future, we can refer to n, and it'll be the pointer to that place.
So the storage of that value into the large memory is implicit within the code?
Exactly right, because what we're doing here, the input to this process is a bunch of text that we will assemble into a file of bits, which when we execute it will get copied into the large memory and then executed. And that set of bits will be data and program, both. And they can be mixed up. Okay, there's nothing saying it has to, the data has to be in one place and the code in the other place or anything like that. Okay, and we use this single simple mechanism of dot and a label with a colon sign for keeping track of where in that file different things are, and also doing jumps and branches. Isn't that neat? So it's a very simple and straightforward thing. And you know, you'll get used to all of this. And again, it's not a thing that you can catch the first time when you listen to it here. But the problem set is tons of fun, and you'll get used to the whole thing there. And it'll all make sense to you. Okay, it turns out to make your programming life even easier, we have made the macros be unique if they have a different number of arguments. And so what that means is that the macro definition of branch, which has a label and a register, is different than the macro definition of branch that has a label. In other words, the macro preprocessor is smart enough to figure out how many arguments did you give when you wanted to do a branch. And depending on how many you gave, it calls up different definitions. Now, let me see if I can give an example of that. I say macro foo of x comma y is x plus 1 plus y. Okay? And then I say dot macro foo of x is x plus 3. Let's say I did those two lines. I have actually defined two different macros. They both have the name foo, but one is a macro of 2 arguments and one is a macro of 1 argument. And so if I say here foo of 3, what would come out would be 6. But if I said foo of 3 comma 4, what would come out? And actually, this is wrong. Would 6 come out of this first part? No, it would come out 3 plus 3. Then the second part would add them together, and it would turn into 6. What would foo of 3 comma 4 turn into? 3 plus 1 plus 4, and then the second half would turn it into 8. Okay? Yeah?
Is there a way to have variable numbers of arguments without
Explicitly saying it? No. Okay? The assembler is pretty dumb. And so what we did is that we made it as smart as it needed to be and no smarter. Okay? So it does not have var args. But it's nice because it turns out that often I want to branch to a certain place, and I don't care about this mysterious register C, which I'm going to talk about in 2 seconds. Okay? And I can just say branch label. And the macro that is for branch label will actually do the right thing. Let's talk about this register C. Why do I have another register? If you recall, branches and jumps are things that, in the case of a branch, adds an offset to the PC depending on the register that you give it. So if I say branch R0, comma, label, comma, R1, what you know so far is that it will test, say this is branch if equal, B branch if not 0, BRNZ. It will test if R0 is equal to 0. If it's not equal to 0, it will jump to the label. And it does that by offsetting the PC by a certain amount that's figured out in the macro for this thing. But all that you really need to know is if a label exists down here and R0 is not 0, the PC will end up going to the instructions that start at this place. Now, what do you think R1 is for? Well, I've hinted at it now 3 times. It's for the same purpose that the continue register was for in that scheme register machine language. It basically remembers where we came from. So what the instruction does, actually, is before it does any of the work of jumping to the PC or even looking at whether or not R0 is equal or not equal to 0, it says, let me squirrel away where the PC is, and if you remember, the PC always points to the next instruction to do after this one, and let me put that into R1. And that means that if you're down here and you want to jump back, you just say branch to R1. Okay? Except that that's not quite right because that means to test R1. So what do we really want to do? We want to jump to R1. Because if you recall, jump was that instruction which takes a register and makes the PC equal to that. And this is a way of doing a subroutine return back to this location right after the branch. So this branch here is a subroutine call to down here, conditioned on whether or not R0 is 0. And this instruction down here is a subroutine return to this location back here. And that exists in every branch, and in fact, it even exists in every jump as well. Jump R1, comma R2, we'll put in R2 this location here, so in case for some reason we want to jump back to here, then we can. Every branch and jump stores where we came from. Every single one. It's so simple, it's universal.
Like it's up there when we do just branch label, or the bottom one.
You got
it's
it.
in R31, which is 0, and so it throws away our current.
That's absolutely right. So the trick is, because you as a programmer often don't care about remembering where you came from when you branch to a certain place, what we did is we defined a macro of branch to a label without remembering where we came from by saying that is the same as branching to the label remembering where we came from in R31, and R31 is where the bits go but never come back, right? And so that's how you write things. Now, it turns out that the hardware of the machine, we have a little intermission here.
Is the purpose of throwing it away just to save register space, or, I mean, it seems like it's...
No, it is just that the programmer doesn't need to store it, so the programmer may be using all 30 of the other registers for something else, and we've run out of registers. And I don't need to know where I came from some of the time. In fact, take a look at this. Here's an unconditional branch, which we actually looked at the last time, and this macro is defined as calling branch if 0 using R31 as the register to test to see whether or not we should, okay? And again, you got to get out of this mindset of thinking that perhaps this is a dumb thing to do, because doesn't it take more time and more work to test a register and then conditionally branch than to do the simpler thing of an unconditional branch, which is what we're trying to do here. And what you're going to learn very soon is that the architecture of the machine is such that all of those things take exactly the same length of time. They all take one cycle to do. And so to simplify things, we only have really one type of branch, which is to branch by testing something. We actually have 2 types, right? Is it 0 or is it not 0, right? But we do need that. And then this is the place we want to go to, and here's where we store where we came from. So if we want to, after a while, we can come back to here. And to make it easier on ourselves, we allow ourselves to put R31 in either the test place or the place where we want to store where we came from, or both. Okay, in the case of this last branch here. Okay, just go to there.
So how does it work where you can only go through one pass in the macro preprocessor and you only have one argument? Will it end up
Yes.
3 in the end or 2 in the end?
Let's see. These are definitions of macros here, right? So there are, in fact, 3 macros being defined. If I were to use the macros, I cannot use the macro BR of one argument up here. But the way that it's set up is that I have a file that you're going to use with all the macros in them that are defined as .macro something. And that will be prepended to whatever code you're going to write. So all these definitions will be before your code. And so the one pass will see them all first. And then you will use branch of one argument, of 2 arguments, of many arguments. But notice that this one is using a macro of 2 arguments, which was defined previously. So that's why you can do it in one pass. Okay? All right, great. Okay, so now let's go back to recursive factorial, or actually let's start with that. Remember in Scheme, the definition is if n is equal to 0, then we return 1. Otherwise, and this is now different than what we did the last time, we do the recursive call to fact of n minus 1, but we still have some work to do after the recursive call gets back, which is to multiply by n, and then we're done. Now, we're going to make a slow transition here from Scheme into C, okay? And you're all going to go, oh, that's horrible. I didn't come here to Cambridge, Massachusetts to learn C. But the truth is that, again, most of the world does not use Scheme. Okay? I really hate to say it. And in fact, the world uses C a lot. And unfortunately, C++ some of the time, at least at Microsoft they do. Java, of course, and God forbid, they're starting to use this thing called C#, right, which is the worst thing of all. But they're dialects of C, and so there's nothing wrong with kind of getting used to the syntax of C. And it turns out that when we're talking about programming computers at a low level, it's in fact kind of handy to use C. And the reason is that assembly and C are in fact not that different from each other, except C is more easy to read. Okay, and so in order to sort of do this without causing you all to waste a huge amount of time, like let me get my book here. There is if you really want to learn C, and I do not recommend that you do this, but if you have lots of time, you can get this book, which is a simple book, but it's a very, very good book called A Book on C. Okay, but this is not a recommended book for the course, and you don't need to do this in any way. It's just if you want to. Okay, this is the author is Kelly and Pohl, Kelly and Pohl. Okay, but it's a thick book, okay? You don't actually need this. But if you want to, you can. What I've done is, and this will be on the website, and I'm going to print this out and leave it in the place. One of the guys who wrote C at Bell Labs in 1974 wrote a tutorial on C, and it's very short and very straightforward, I think. And so you can look at this too. You don't even need to read this, okay? The other option is to just watch and learn, okay? Because I'm not going to be doing anything in C that is that hard. And basically, what we're going to be talking about in this course is how simple things in C might get translated into instructions that a computer would execute. And then very quickly, we're going to talk about the hardware implementation of those instructions themselves. So we're not going to spend very much time on the C stuff. But if for any reason you're puzzled about what a certain line in C might mean, like these are all pretty clear, right? Int fact of int n. Well, what does int n mean? Well, n is an integer, okay? Int fact, that means that fact is going to give back an integer. Okay, so this is just the declaration of fact, and unlike Scheme, which doesn't have types, right, that you define specifically unless you really want to, in C you have to say what the argument is and what the function is going to give back. So take an integer n, give back an integer as a result. Curly braces as opposed to the parentheses in Scheme if n is equal to 0. So here again, it's an infix as opposed to the prefix that you see in scheme. Anyway, check if n is equal to 0. If so, return 1. Otherwise, you return n times fact of n minus 1.
Where can we pick up the tutorial?
That'll be sitting out on the table, and we'll also put it on the website for the course. Okay? But I would like you to kind of think of it as a reference to look to if you need to. But for God's sakes, don't think of it as something that you need to learn. Okay? Because really, it's not that hard, and just think of it as in those terms. Okay, so with all of that said, both of these functions are trying to do the same thing. They're just trying to do the recursive version of factorial. So let's say, how could we actually execute this with these instructions we've been talking about the last time and today? Well, before we said that location n would be somewhere in the main memory. This time, let's actually say that it's in a register. Let's say in R1. We'll put the argument n in a register R1. And when we're done, we'll leave the value in another register, let's say R0. And we're just making this up. We can make up any rules that we want. Well, it's a subroutine call. We're going to call factorial, and we expect factorial, when it's done, to return to us. Meaning that if I'm a program, I want to branch to factorial, and I want to somehow remember where I'm coming from so that when factorial is finished, it can come back to us. Well, it turns out that there is a convention for a register to use for that kind of linkage, just like the continue register was used for scheme. And that register is R28. Now, what we're going to do is we are going to define the symbol LP to be R28 so that you don't need to remember that R28 is in fact going to be used for this. And what LP stands for is the linkage pointer. And by linkage, we mean the way that I will link between the caller of a subroutine and the callee. So the caller will link to a subroutine that's going to call, saying, before I branch, I will store the result in R28. Branch fact, comma, R28. And then R28 will end with jump R28, and then R31, which just throws away what's after the jump, which is fine. Okay, so this is the linkage between a caller and the callee, how you get back from a subroutine call. So this looks good, right? We can call fact and we can get back from fact. Except, when you think about it a little bit, now here you see I've gotten rid of the scheme and I'm only using C. Little sleight of hand there. What happens when fact calls itself? We said that n is going to come in R1 and the result is going to come out in R0. If I branch, oh, and wait a minute, and the linkage is going to be held in LP. So there's 3 errors here. First of all, the linkage pointer, like the continue register, is only one place. So if I call fact and fact calls itself, as soon as fact calls itself, what is in the linkage pointer? Is it the way back to me, or is it the way back to fact? It's the way back to fact, right? Because there's only one word being used to store things. What's wrong is that we only have one register, this LP. And a subroutine that either calls itself or calls another one needs another place of storage, because we have to remember a chain of places that called each other, not just one. And so, of course, what we need, as you learned about when you did the scheme stuff, was that we need a stack. And the stack is going to be the place where we push on where we last came from, so that we can add more and more things, and so we can have a chain of subroutines that call each other. So here's what the stack's going to look like. We're going to have, let's say we do fact of 3. We're going to have a place on this stack which is going to be for storing data related to n equals 3. As you saw in the recursive version, n equals fact of 3 calls fact of 2. And we'll have a place to store linkage for fact of 2. That's going to call fact of 1. We'll have a place to store the linkage for fact of 1. That will finally call fact of 0. We'll store some stuff for that. That will hopefully resolve to be 1. And then we'll return from there, we'll return from there, we'll return from there, and then we'll be done. Okay, but we'll have this expandable storage for storing linkage. Turns out we'll have to store other stuff too. In general, we need to store the arguments. When we call a subroutine, in particular if we call ourselves, and the arguments for the call are different than the arguments that we got called with, we don't want to forget the ones that we got called with because we may have extra work to do after the call comes back. And so that's what you need the stack for. So let's talk about this more specifically. I talked about this a little bit the last time, but in general, we're going to think of the stack existing in that same big, slow memory just like we had before. And as I drew on the board there, the nomenclature we use is that the lower parts of the memory are up here, and the addresses go up and up and up as we go down the page. And the way that we're going to grow the stack in this class, and some processors grow the stack the other way, but we're going to grow it in such a way that we're going to reserve one of the other registers for what we're going to call the stack pointer. And it will be an address of a location in memory that is free where we can put the next item on the stack. And when we want to push something on the stack, we'll place it here, and then we'll increment the stack pointer to point to the next place. So every push will add something to the end of the stack, and the stack will grow in addresses which increase down the page, which means that the newest stuff is going to be at the bottom of the page at an address that is as high as any of the things are. And the older stuff will be at addresses that are lower but more towards the top of the page. Just like I've drawn here, we start at 0 and we increase on the way down. Okay? So, in general, what will be done, let's see, did I actually tell a lie? Stack pointer points to first unused location. Oh yeah, no, I didn't tell a lie. But there's a messiness here that we should probably not even talk about now. Let's not even talk about the lower left-hand part of the thing there. There are macros for pushing things and popping things off the stack. So first of all, just as R28 is going to be this linkage pointer called LP, and whenever we jump to a subroutine, we'll remember where we came from in LP, which is the same as R28, we're going to reserve R29 for the stack pointer, SP. And the macro push of a register will be a macro which expands to two other instructions, themselves macros, which will basically say increment the stack pointer by adding 1 to it, and then store the register that we're trying to push onto the stack by going back from where the stack pointer is now. And this is actually the slight strangeness that I didn't want to go into, but I guess I have to. So let's talk about what's going on here. Okay. We'll draw a new picture here. Here's the big memory of the machine. And here's low addresses, and here's high addresses. And I just told you that no matter what is on the stack pointer will point to the first unused location on the stack. So remember, this is contents of the stack pointer. And that's equal to contents of register 28, because stack pointer is just a symbol for R28. Oh, I'm sorry, 29. 29. Thank you. But this is going to be free. When I want to push something on the stack, I'm going to do it in 2 steps. You may think the first step should be to put the thing in here, and then the second step should be to add something to here. Okay, but it turns out that that's bad. And the reason that it's bad is that if I do that, when I'm done with the first step, but I haven't done the second step of incrementing the stack pointer, I have left the stack in a state that violates the rule that the stack pointer is pointing to a free thing. And later on in the course, we're going to ask ourselves the question, what happens if the computer is interrupted in between the 2 steps? And if it's interrupted in between the 2 steps and the interrupting process adds something else onto the stack, it may actually smash the value that we have half added on. And so to be safe against that, we'll do the 2 steps in reverse. We're going to increment the stack pointer first, and then we will say, look backwards and add the thing in this place here. And that way we're guaranteed that the stack pointer is never left pointing to a thing on the stack that we want to keep. It's always pointing to the next free space. Okay, and it's a subtlety that you really don't need to know now. And I'd wanted to skip it, but anyway, that's why it's done in that way. Now notice that we use this incredible handiness where loads and stores can indicate a constant offset from the contents of a register that they're using to point into the big main memory. So that's why we can get away with add 1 to the stack pointer and then store that register into where the stack pointer points to, but 1 back from there. Okay? And in the same way, pop works the same way. And then we have 2 other subroutines, which are pretty neat, which say, you know, I want to allocate a whole bunch of stuff on the stack. Let's say I'm about to call, or I'm about to execute a subroutine, and it has 100 bytes, or 100 words, excuse me, of local variables. I don't have to push 100 times. Instead, I can just say add 100 to the stack pointer. If this distance is 100. And I can do that by saying allocate 100. So that's a macro too. And then when
reserve space, it doesn't
right,
fill the space.
It doesn't fill the space. There is junk there. Okay, so I just said bump the stack up by that much. Or I can take away that much space from the stack by subtracting a constant from the stack pointer, putting the result back into the stack pointer. So one would think that usually when you do this, you take away that. Okay, so now let's kind of back up again and think about the stack. The stack is going to be this really centralized storage mechanism that we're going to use for doing function calls. It's really, really a nice thing, okay? It has the characteristic that, of course, the first thing in is the last thing out, and the next thing out is the most recent thing that you've pushed on. But it turns out because functions call each other in a hierarchical way, that stacks are just perfect for that. And so, in general, the stack pointer will point to a free space, like it does here, and what will be on the stack immediately older than that free space that it points to are sort of 3 types of things. One will be, what were the arguments to the procedure that is running now? Those will be on the stack. The second thing will be the linkage. How do I get back? How do I return to the procedure that called me? And then the third one will be, what are the local variables that I, as a procedure, have that I want to have my own private copy of? So that is what our stack frame is going to look like every time. And if a procedure calls another one, we'll build this up again. And if that one calls another one, we'll build it up again and again and again and again. And when that procedure returns, we'll pop that off, return, 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 each time taking off this whole stack frame, which again will consist of those 3 parts: arguments, linkage, and locals. Alrighty. Turns out just about every computer that's made these days has a stack mechanism like this, and just about every language that's out there has organized the idea of storage with regards to a procedure around the stack. It's a little bit of a shame that in Scheme you didn't get to see this. Okay, the idea in Scheme was that the variables came into existence kind of on their own, and a garbage collector went around and scooped them up. And the order didn't matter very much. Well, it turns out that you can handle the allocation and deallocation of most storage in a simpler way, which is to use a stack. Okay? And it doesn't mean that you can't have a heap also, the way that you have in Scheme, but the stack is used in most cases for most of the storage that goes on. All right. Now, in this course, we're going to allow you to freely mix the program and the data that the program uses, the constants, the variables. But typically, most uses of these things put the variables in a second place. In other words, this is the code, and this is the data. And then there's a third space, which is for the stack. And you want to make sure that as the stack grows and shrinks, that it's not going to bang into any of the other things that are out here. So in all of our stuff, we will, in fact, put this stack safely away from all of the other things that are going to be used, because the stack pointer is going to be going up and down, and we don't want it to hit anything at all.
When you run multiple programs, do you share the same stack?
That's a great question. In general, no. Okay. You sometimes share the code. So there are many different ways of thinking about this thing. In a language like C, the most typical thing is if I'm running 3 copies of a program at one time, then the memory associated with the program will be shared. And so there'll only be one of those things running. The variables will be separate and the stacks will be separate. A language like Java has this idea of a thread, okay? And a thread is something where the variables are shared and the code is shared, but the stack is not shared. Okay, so that's sort of yet another thing that you could do. People have played around a lot with what you should share and what you shouldn't share. But for now, till sort of another few weeks into the course, let's only think about just one of these things going and what it does.
Now, it looks like since we actually the data in the stack is contiguous.
Yes.
And the stack pointer increments, it looks like by one each time,
yep,
that we actually could access data that is not on the tip of the stack.
Oh, that you could be bad and you could kind of go backwards and kind of see things here. Yeah.
Is that just bad,
bad
programming to do that? Or?
Most let's see. What we'll talk about in the pretty close to the end is a system where the different parts here, so typically, let's say that this is the stack and the programs here, there's usually a gap between each of these segments here, okay? And it's also typical that the memory protection hardware will not allow the stack pointer to look at this other stuff here. For now, we're not going to worry about that at all, and we're going to assume that it, in fact, could do that. But towards the end of the course, we'll talk about how we will prevent the abuse of the stack pointer to look at other things.
Or not necessarily other things that are outside of the stack, but other things that are in the stack rather than being on the end of the stack. For example,
oh, I see what you're saying. Oh, okay.
On the stack for data blocks.
We are going to do that all the time. In fact, we're going to do it probably in the next slide.
Without having to pop?
Without having to pop.
Okay.
So let me make it clear. Just because we're using a stack does not mean that this is a zero address system. It's not that we say add and it takes the last 2 things off the stack and puts the answer on the stack. We're going to use the stack pointer to access data throughout the stack here. So we're going to, if we want an argument, we're going to say, let me look so far back on the stack and do a load so many words back. And in fact, that's going to be one of the best uses of the constants in our loads. So let's talk first, though, about using the linkage pointer and the stack pointer. Typical thing, if we want to do a call, we say branch to a function f with the linkage pointer. If we want to be careful about that and make sure the linkage pointer doesn't get destroyed by the next call that happens, if the caller calls another function, then what we've got to do is, if we're going to call another function in here that might trash LP, in general, we will surround it with a save of LP and a restore of LP, to use the same language as the scheme book. What that is a push of LP and a pop of LP. So in here, we can go ahead and smash LP as much as we want, because we know here we'll restore it from the value it used to have here. And then finally, when we return, it's safe, because we know that we're going to get the value that it had when we pushed it on here, because we popped it off here. So pushes and pops are in general used to safeguard a variable that can get overwritten in the middle. So let's kind of go halfway. Let's assume that we're going to, again, pass the argument n in register R1. And let's assume that we're going to return the result in register R0. And so we're not talking yet about putting the arguments and the results on the stack. We're only going to put the linkage on the stack. Well, the first thing we're going to do in our recursive factorial subroutine is we're going to save the linkage pointer. That will get us out of this problem that we had, that if fact calls itself, it destroys the information as to where to go back to. So here's push of LP, and notice here, here's pop of LP. So this corresponds to that and safeguards the fact that LP may get destroyed in the middle, so that when we jump back to whoever called us here, we're jumping back to the LP that got saved here. And so that's great. So now we're free in this code to smash LP as much as we want. So what do? We compare R1 to see whether or not it is 0. That's looking at n. And if it is 0, we go to fact 1. Fact 1, we move the constant 1 into R0. That's where we decided the result's going to be. And then we branch to fact x, which just goes back to here. And then we do pop of LP and jump to LP. So in this case, the saving of LP was not actually necessary. Okay? But usually the way these disciplines work is that you decide the very first thing you're going to do in the preamble of a function is save away the registers that might be wrecked. And so we're going to just save LP, and in the postamble, the last part of a function, we will restore LP and then jump to it. And so therefore, the meat of the code here, which is the case in the terminal case when n equals 0, is to return the constant 1 into R0, branch to fact x, and then do a subroutine return. In the middle, if we're not in fact going to do that, what do we need to do? Well, we need to call fact of n minus 1, except for one problem. Down here, after we're done calling fact of n minus 1, we need to multiply n times the result of fact of n minus 1, and we need to return that. Which n do we need to multiply by fact of n minus 1? The n that we were called with. So we need to be careful and make sure that we save n and restore n because we're just about to subtract 1 from it. So here the second use of the stack comes in, which is that we're going to call ourselves, but we're going to change R1, so we better save R1 and restore it here so that after the call, the multiply can get done of n times fact of n minus 1, and then the return can happen. So that's the purpose of the push and the pop here. Finally, in the middle, we just subtract 1 from n, which is being stored in R1, and then we call fact by branching to fact using the linkage pointer as the place where we came from. Okay, so it will store into LP this place right here, so that when fact is done doing its thing and the next call of fact does this, it'll come back to here, multiply R1 times R0, putting the result in R0, and then come down here and return to whoever called us. Okay. So, it gets even fancier. But again, it's just like, you open the hood of a car and lots of wires are there, right? But there's air, there's gas, and there's spark, and that's all there is, okay? So really all there is here is arguments, linkage, and locals, okay? Only those three things. In general, we will not be passing the arguments in R1 like I just showed you there. That was just to sort of do a half step here. What we're going to do, in fact, is when we want to call a subroutine, the arguments to the subroutine will be pushed on the stack. And that's much better than saying I'm always going to pass them in R1, because we may have a lot of arguments, okay? And they may not fit in the register file. So we're just going to say the arguments are just pushed onto the stack, and then we're going to call the subroutine, and all kinds of linkage is going to go on here. And then once the subroutine is running, it may want to have some space for local variables itself, for its own private copy of them. And those are going to get pushed on the stack too, and then we're going to have the stack pointer down here. And what we're going to do to keep track of this, because this stack pointer, this poor stack pointer, is going to be jumping up and down all of the time, we're going to say, you know what, it would be easier for us as mere human programmers to have another pointer into this mess that's on the stack. So that when I'm in a function and I want to access a particular argument, or I want to access a particular local variable, or even if I want to access a particular piece of linkage, that I have a fixed index tab into the stack from where I can reference all of these things, and that's not going to move. As long as I'm inside of a function, this index here will not move, even though the stack pointer is going to go up and down each time I push and pop things. And that thing is going to be called the BP, which is the base of frame pointer. And it's going to be yet another magic register. And we could define these however we want, but the BP is going to be register 27. Okay, so we're starting to eat up all of our registers. But it turns out that these are the 4 that are the ones that we're going to use. Okay. SP we know of, R29 is a stack pointer. LP, R28 is the linkage pointer, what we're going to use whenever we want to do a subroutine call and come back. And then R27 is going to be this base of frame pointer. And the difference between BP and SP is that when we do a subroutine call, we're going to set this thing up, and then we're going to leave it there for the life of the subroutine. So whenever I want to get access to the nth argument, I know I go a fixed distance from here, and I find it. Otherwise, I have to keep track how many pushes were done and how many pops were done and where am I now on the stack. And that I won't need to do. So the base of frame pointer is a thing to simplify access to what's called the stack frame, all these different things that are on the stack.
So is there going to be a new base of frame pointer each time we do a recursive call of backs?
Absolutely right.
Okay.
Absolutely right. And in addition, there's this thing called the XP, but we'll talk about that later. That's for when something goes wrong, and it's called the exception pointer. The first thing that we're going to do is we're going to push the arguments onto the stack. And if there are n of them, we're going to push them all on. And it turns out that if we actually have two choices here. We can push them on from the first to the last, which may seem like the natural thing to do, or we may push them on from the last to the first, which seems like the unnatural thing to do, but is actually the right thing to do. And the reason it's the right thing to do is because we don't, in some cases, know how many there are going to be. Some functions are written that take a variable number of arguments. And so a caller may call a function with 3 some of the time, or it may call it with 6 some of the time. And usually the way this is set up is that as long as the function that's being called knows where the first one is, it can figure out how many more there are to go. And so the advantage of pushing them on in the reverse order, or as they say from right to left, is because, again, looking at the stack frame, backing up here, if I know where the base of frame pointer is here, and argument 1 is over here, I always know what this distance is to get to the first one. And then the question is, how many more will I do backing up to get to the nth one? And it's okay if I don't know how long this is, as long as I know how to get to the first one. If I'd push them on the other way, 1, 2, 3, 4, 5, up to n, I would have no way of knowing, as the called function, how far back to go to get to the first one. So anyway, that's the reason for putting them on in reverse order. Okay, once I've pushed those all on, I branch to the function using the linkage pointer. So now here I am at the function. The preamble of every function will look like this. I just got called. And this linkage pointer LP is a precious thing because it tells me where to go back to. And God forbid I should lose it. So the very first thing I'm going to do is squirrel it away on the stack. I'm going to save it. Save this linkage pointer. Now I'm a new call of a function. I'm going to set up a new base of frame pointer, which is that little tab saying what my stack frame looks like. And that's going to be different than the base of frame pointer of the one who called me, so I'm going to save that one too. And for these two pushes, notice there are these two pops down at the bottom. Okay, so here's the rest of the function. This push of BP lines up with this pop of BP. This push of LP lines up with this pop of LP. And when I'm all done, I'm going to jump to the linkage pointer, which is a subroutine return from where I've gone to. Yeah?
Wouldn't we be, I mean, the contents of the BP right now are the BP from the last call, so wouldn't we need to like push the stack pointer?
Pushing the stack pointer doesn't actually do anything. You see, the stack pointer is always growing down when we do pushes, so we never really need to push the stack pointer.
Right, but what I'm wondering about is the base of the frame for the function we just entered. We're pushing the base pointer, the contents of the BP register, which we haven't set to anything.
Okay, here is the mix-up here. This BP is actually what the BP was in the function that called us. Notice the function that called us didn't save the BP.
Okay.
It just assumed, so it is doing this on
one.
behalf of the person that called us. Okay. Right. And of course, in designing this thing, there is a choice. One can do it here or one can do it down here. And we just chose to do it here. Okay? Now, having squirreled away the BP, we're now free to trash it. And what we're going to do is we're going to say the BP is going to be where the stack is right now. And this will be our reference tab for the current stack frame. And we're going to move the stack pointer to the base of frame pointer. We make a copy of SP and make BP where the stack is at this point. Having done that, we make space for locals, other registers, any other work on the stack that we may want to do. When we're all done, we pop whatever we used off. It turns out that although functions often have a variable number of arguments, at least in C and even in other languages, it's often the case that the result is not of a big size. The result of a function is often something that's a single word. So we're actually going to keep the somewhat backwards convention of putting the result in R0. So a function is typically expected to produce its answer and put the result in R0. Having done that, we're going to say move BP into SP. What does that do? If you remember, the base of frame pointer was set to SP up here, so this is a complement to this thing here, which basically says, let's put the SP back to where it was right here. And having done that, we just pop off BP, pop off LP, and then we are done.
So the move command copies the first argument
to the second one. Right. Okay. And guess what move is? Move is add C, register A, R31, register B. Add 0 to a register, putting the result in another register. Here's a stack frame. Okay. The arguments got pushed on first in reverse order from n minus 1 to 0. That means that it's easy to figure out where the first argument is by subtracting 1, 2, 3 from the base of frame pointer. This is where we should go back to, the caller's return PC. This is what the base of frame pointer was in the stack of the subroutine that called us. In other words, this is a pointer back to the index tab for this stack frame. Okay? Then comes the local variables, and notice that after we pushed BP on, we said move SP to BP, so we established that the index tab for this stack frame is going to be right here. Will always be right here. A pointer to the first local, those get pushed on, and then there is free space here, and here's where the stack pointer is. But this may bounce up and down, but the base of frame pointer for our function will stay here. Okay? Again, it's hard to grasp this all now, but doing problem set 1 will help you a lot. How do you get to the jth local variable? Well, all you need to do is say, this is a little bit messed up here, load base of frame pointer, comma j, comma rx. Now, is that actually right? Here's the base of frame pointer. What does it point to? The 0th local variable. So if j is 0, we load what is in the base of frame pointer plus 0, because if you remember, load works that way. This left parenthesis shouldn't be there. This should be BP, comma j, comma rx. This is why this is bad. I can't write on here. But anyway, it adds j to BP and uses that as a location on the stack to find the local. Sure, that is exactly the right thing. To get to the first local variable, it's BP plus 1, BP plus 2, BP up to n minus 1. And to store it, you, of course, do the same thing. So this is really great. The base of frame pointer points to local variable number 0. How about the arguments? Well, if I want to get to the jth arg, I say load BP, comma 3 minus j, comma rx. What's that do?
Bill,
yeah.
it should be minus 3 minus j.
I'm sorry. Good. Okay. That's very smart. Minus 3 minus j. Because what I need to do is I need to go backwards. First of all, 1, 2, 3. And then I need to go backwards j args in order to get to the jth argument. So that's a typo also. Yes. Good. And for storing, that would work in the same way. Now, what's important here are two things. One is you're beginning to see the use of this base of frame pointer because it points to a fixed place in this stack frame to access the args and the locals. Second, you're beginning to see the cleverness in having a load and store that can do a little bit of work for us in terms of adding a constant to a register before figuring out where it wants to do the load and the store from. And so this is a really neat way to get things from the stack, and answers your question, which is that we are not only going to be dealing with the top of the stack, but in fact we have our hands all through the current stack frame. Okay, great. Okay, there is a contract, as there is in many pieces of software, having to do with the stack. The contract is that the caller pushes the arguments onto the stack in reverse order, branches to the callee, putting the return address into the linkage pointer LP. After it's done, it's responsible for removing the arguments onto the stack that it pushed on. The callee, on the other hand, will perform the computation, leaving the result in R0. It will branch to the return address that was pushed on, that was given right here, this LP. And here's the key thing. The callee will leave all the registers except for LP and R0, of course, because this is where it's going to give the answer back, and this is where it's going to jump back to, but it will not damage any of the other registers. So when a caller calls a function, it can assume that the other registers, R0 through whatever, will survive the call. Okay, they will all survive. And that's incredibly important because it sets the contract of why the callee actually does all this saving on the stack. You'll notice, in fact, that this does not say that the callee is going to push LP, is going to push BP, is going to do all this other stuff that it does. But it, in fact, does that. And why does it do that? In order to ensure that this is true. Okay, so the contract doesn't specify that kind of stuff that gets done, but that's in fact what it does. Okay, now let's look at factorial done the right way. This is the full method here. What's the first thing that we do? We're going to save LP and we're going to save BP. Then we're going to establish our base of frame pointer by moving SP into BP. Then what do? We push R1. Why are we doing that? Preserve registers. Because of that last item in the contract. The last item in the contract says if you're going to destroy a register, you better restore it. So here we surround the fact that we're going to use R1 as a temporary with a push and a pop, and inside of here we use R1 freely. Okay. Load base of frame pointer -3 R1. This is essentially finding the argument n, if you remember that's going to be 3 up on the stack, off of base of frame pointer and putting it into R1. Check if R1 is not equal to 0, and if it is, then n is big, so we go down here. Otherwise, we move 1 into R0, which is where we're going to return the result, and we branch to return. If n is greater than 0, then we go down here, we subtract 1 from n, we push that value onto the stack, because that's going to be an argument for a recursive call to ourselves. We branch to fact comma LP, so we go ahead and we reload what n was and we put it back into R1. Because we can depend on that n still being the same on our stack. We multiply R1 times R0, which is n times fact of n minus 1, putting the result into R0, and now we're done. And so finally we can do the return, which is popping R1, which we saved up here. So now we've obeyed that last line in the contract that says do not destroy any of the registers other than R0 and LP. Restore the stack pointer to where it was up here. Move BP to SP is the inverse of move SP to BP. And then pop BP, inverse of push BP, pop LP, inverse of push LP, and then jump back. Then we're all done. So this is sort of a little typical post-amble that we would put on a subroutine, and this is a typical preamble that we would put as well. And this is the code that goes in the center. And that's it.